Okay, so what is the disjoint path problem? It says given a directed graph and a start node S and a finish node T, we want to find the maximum number of edge disjoint paths from S to T. And two paths are edge disjoint if they share no edge in common. Now, if you think about this on the internet, this is something that you might like to do. Why would you want to connect? For example, suppose you're connecting to a download site. Suppose T is a download site, and here you are. Why would it be nice to have disjoint paths to a server at T?
Get more reliable, and if you care about it, a more secure connection.
Okay, you could get more. Why would it be more reliable?
One of the links might go down.
Because if one link goes down, you still know you have another path, right? So why would it be more secure?
If somebody's eavesdropping at one of the nodes, they only get to look at some fraction of the total traffic.
Good. So if we split the data between it, they could only get partial information and may not be able to reconstruct it. Okay. And what's another reason why it's good to have disjoint paths? How about the speed? How about the bandwidth? Would you get more bandwidth on disjoint paths?
Yes, sure.
Yeah, because typically the bandwidth is limited by the slowest link, right? So if I have disjoint paths, I can essentially double my bandwidth. Okay. And this is generally what's done, right, with BitTorrent, for example. BitTorrent is often finding disjoint paths and downloading from multiple locations. Okay. Okay. So here's two disjoint paths. I don't know if you can see the colors. We have a blue path from S to T, and then we have a purple path from S to T that's disjoint. They share no edges in common. They share vertices in common, but no edges in common. Okay. Okay, so we mentioned this idea of having more reliability, and we have this idea of network connectivity, which we can define as being the minimum number of edges whose removal disconnects S from T. Now, we just said if we had two disjoint paths, any single edge could not disconnect S from T, right? So we could ask, well, in this graph, what's the smallest number of edges that we could remove that would disconnect S from T? So if you look at it here, there's exactly two edges whose removal leaves S disconnected from T. Does everybody see that? Okay. So there's something going on here between the number of edges whose removals disconnect the graph and the number of edge disjoint paths. And in fact, this is true in general. And the theorem, which is often called Menger's theorem, says that in any directed graph, the maximum number of edge disjoint ST paths is always equal to the minimum number of edges whose removal disconnects the graph. Okay, Menger's theorem. It says the disconnection value is equal to the connection value. Okay? So let's see if we could prove this. One part of this is easy. The part that says the minimum number of edges whose removal disconnects the graph, I can't have more paths than that. You cannot have more paths. So, in fact, the number of paths has to be less than the disconnection value. Why is that? Well, suppose you had that disconnection. Okay? Well, notice that all the paths have to use at least one of those edges. Right? If it disconnects, every path has to use one of those edges, so there could be at most k paths. Okay? And notice in this example, I had two edges. Notice both paths had to use one of those edges. The harder part is the converse, which says that the maximum number of the maximum number of disjoint paths. The maximum number of disjoint paths is at least as large as the minimum number of edges whose removal disconnects the graph. And so let's see why that's true. So suppose the maximum number of disjoint paths is k. What we could do is visualize those k paths as each sending one unit of flow. Okay, so think about this as a data network, and you could think about each disjoint path as having some flow of data, one unit of flow on each path. Okay, so that's the way we're going to be thinking about these things as flow through a network. And we're going to prove today something called the max flow min cut, which says that the maximum flow you can get in a network is equal to the minimum value of the cut. Now, what is the cut here? A cut is simply a partition of the partitions of the nodes of the graph, and then the value of the cut is going to be the number of edges that leave A and go into B. Okay? And in fact, this is going to be an ST cut, because we want S to be in A, we want T to be in B, and the cut is going to be simply the number of edges that leave A into B. So here's a picture of that cut. So I have A and B, and the value of the cut is the number of edges that leave it. Okay? And so the maximum flow is equal to the minimum cut. So what that proves this part. This part of Menger's theorem follows from the max flow min cut theorem. Okay. Now, Menger's theorem is a very nice thing to remember. It's such a simple statement, and not only does it apply to edge connectivity, it applies to node connectivity. What does that mean? We could look at the maximum number of node disjoint ST paths, and that number of node disjoint paths is equal to the minimum number of nodes that I would remove to disconnect the graph. So Menger's theorem applies to both edge connectivity and node connectivity. And to get some engagement from the class, I'd like you all to try to apply Menger's theorem to this graph. So if you have a piece of paper, I'd like you to take out a piece of paper and find for me this equality for both edge connectivity and node connectivity. And I'll even tell you what it is. The node connectivity is 3. So what does that mean? The node connectivity means 3, means that there's a removal of 3 nodes that disconnect S from T, or in this case V from W. And any 2 nodes doesn't disconnect it. That's what 3 connectivity is. And I could find 3 node disjoint paths. And likewise for edge connectivity, I can find 5 edge disjoint paths, and I can find 5 edges that disconnect the graph. Okay? So let's just spend 2 minutes and see if you can apply both of Menger's theorems to this example graph.